Hello everyone, my name is Matthew Leha and I'm here with Yuna Lee, and today we're going to be talking about the quadrupole mass spectrometer. So first thing off is, what does this thing do? All right, the mass spectrometer, the easiest way to think about it is it's a mass filter. All right, so when it's activated, any ions that enter this field will experience its potential difference that either will end up deflecting them or allowing them to continue on their original trajectory. So the ions have to pass between these four metal rods. These four metal rods are electrically connected, but they're electrically connected, and on each side they're either both positive or both the negative. And depending on the mass to charge ratio of this ion, it will either be affected by this charge or it will not be affected. And I'll explain what that means here in a minute. But by combining the alternating and direct voltage on these rods, it's possible to ensure that only ions of specific mass to charge ratios are capable of reaching the detector at the end of the machine. So the spectrometers generally have set intervals where it releases a radio frequency scan that will only have one mass charge ratio resonate with the field, which basically means that we can control this machine to focus on one certain type of mass charge ratio. All right. So by calculating the charge of the ions that are pulled through this ion current, uh, that can be detected through this machine. We can therefore measure with an amplifier the information of the mass that was analyzed. So real quick, this is what the quadrupole mass spectrometer looks like. So as I was talking about beforehand, this is a side view of it. But on the other side, there is another metal bar or another metal rod that runs at the same side with this rod, and they'll both either be positive or negative. This one will say that this pair will be positive and that these two right here will be negative. So depending on the type of charge that we give them, they decide on the specific type of mass to charge ratio of ion that we'll allow to pass through. All right. So, and over here, you can find the detector as it runs through the entire process, but I'll continue to show you what everything looks like. So, as I explained before, when we're talking about what samples does this machine use, it excels at the applications where we're looking for particular ions. All right. So we stay tuned on a single ion for extended periods of time. So one place where this will be useful is in the process of liquid chromatography mass spectrometry or gas chromatography mass spectrometry, where they serve as exceptionally high specificity detectors. So this single quadrupole mass spectrometer, usually what it's looking for the entire time, it's just looking inside the residual gas analyzation for the specific voltages, which is the same charges I was talking about beforehand, but it's looking for the different voltages. It's filtering them, and at the end, it's going to place everything onto a specific graph, showing us where the relative intensity is at its peak. So real quick, one more time, here's another view, and it's a better view of showing you all the four rods. The rods that are connected together electrically have the same voltage. Either these two will both be positive, or these two will be positive, or these will be negative, and these will be negative. It just depends, but depending on the intensity of the electrical field, the ions passing through, as it shows here, will either pass all the way through if it's the one we're looking for to make it to the detector, or if they do not correspond with it, they will run into the rods, all right, and they'll stick to it. Therefore, just not even make it to the detector. They will not be detected at the end of the experiment. So I know this is a lot of words here, but it's just a large description of what I was talking about beforehand. So the general process for a spectrometer, it's a machine. Not necessarily, it's not something we control the entire time. We can control certain aspects of it, but I made a huge description of what it is. So basically, it is four parallel metal rods that are connected electrically. They give off a radio frequency voltage that reacts with this DC offset voltage between each of the pairs of the rods. And the ions that travel down these rods, they only certain mass to charge ratio ions are allowed to reach that detector at the end, like I was talking about beforehand in the picture. All right. The other ions, they're considered unstable. They will collide with the rod at the end. All right. Now, the selection of ion that is permitted with this particular mass to charge ratio is something that us, the operators, can scan for it. We can scan for this range of the mass to charge values by continuously varying the amplified voltage. So like I said beforehand, we're looking for the relative intensity that is perfect with the one ion that we're looking for. All right. So if there's any small variations on the ratio, the large effects on the overall resolution in the peak shade will be resultant. And I will explain what that means here in a second. So just one more quick look. If it's the ion that we are looking for with the right mass to charge ratio, it will make it over to the detector. But if it is not, if it's the non-resonant ion, it will crash into the rod and not be detected at the end. All right. And that's all by fluctuating the different charges. All right, so what type of measurements is it making? Again, it's using the mass to charge ratio mentioned before to detect the relative abundance of this high mass to charge ratio ions that pass between the positive rods and the low mass to charge ratio as they pass between the negative rods. Our goal is to find that sweet spot. All right. By increasing or decreasing the electrical parameters that we have, we can either raise or lower the relative value on a scalar axis where this criteria will be met. It's just important to know that whatever is changed, this criteria point will always be specified at that given point in relation to the change of the charge that was made. All right, and right here, I found a picture of a glucose ion as it's passing through the spectrometer. As you can see here, right in between this hash before 80 and at 80, our relative intensity right here is at 100. It's at its absolute peak. That tells us, the operator, that this is where that criteria is the sweet spot that we're looking for. All right, this is where everything's perfect. This is where the relation intensity, better known as the retention time, is going to be at its maximum. And in comparison, as we're beginning, you could see as the values start to spike here and there, we're getting an idea of where the perfect ion is going to be. You can see it starts to increase as we get closer and closer. And right here, we have a big spike come up here. But only here is it where it's perfect. But afterwards, it starts to decrease and it's nowhere close to what we need. So us as the scientists, we're able to depict that this ion at this certain intensity at a certain mass to charge ratio is at its best. It's just where it's perfect. All right, so what can we control? Like I mentioned before, we can control these electrical parameters that depict which ions are going to be allowed to pass through. We're able to control the size of the ions that are affected by this electrical field, or the amount of ions that will reach the detector. So the positive DC voltage will repel positive ions. If we increase its frequency, more ions will be deflected, basically. And it's the same with the negative, all right? But it's important to note that if the frequency is too high or it's too low, ions will simply just pass through. All right, it's not going to be affected, or they will be driven to the rods without being detected. That's just the way it goes. So we have to be very careful about how much we change it and how much we keep relatively the same.
Now for the performance of the quadruple mass spectrometer. Since the quadruple mass spectrometer is one of the most simplest, most affordable, and the most robust mass spectrometer, quadruple mass spectrometer has an accuracy greater than 100 ppm, precision around 90.6%, low resolution less than 3000, and limited mass range up to 3000 atomic mass rate. For the quadruple mass spectrometers, the low mass abundance sensitivity is typically around 0.5 times 10 to the negative sixth, and while the high mass abundance sensitivity is around 1 times 10 to the negative seventh. Now for the real world application. This experiment's title is Identifying the Unknown Byproduct in Drinking Water Using Comprehensive Two-Dimensional Gas Chromatography, Quadruple Mass Spectrometry, and In Silico Toxicity Assessment. This experiment was about the improvements in extraction and detection technologies have increased our abilities to identify new disinfection byproducts, which is also known as DBPs, over the last 40 years. However, most previous studies combined DBP identification and measurement efforts with toxicology to address concerns in few expected DBPs, making it difficult to better define the health risk from the individual DBPs. First, why were the quadruple mass spectrometers used in this experiment? Well, using the quadruple mass spectrometer combined with OECD QSAR toolbar was developed to allow unknown volatile and semi-volatile DBPs produced during different raw water disinfection process to be identified and prioritized. Which samples were used in this experiment? The raw water that was used in disinfection experiment was collected from an inlet of a drinking water treatment plant in Beijing City. Water samples were filtered through glass fiber and stored at 4 degrees Celsius until use, but did not exceed 2 days. The data was presented in the experiment were first, the Venn diagram illustrating the distribution of DBPs in different treated water samples. The numbers represents the number of DBPs in each sample, and overlapping parts demonstrate the number of DBPs that are identical to 2 or 3 samples. The middle graph shows the number of DBPs representing different chemical classes in different treated water samples. The far right graph shows the cumulative peak volumes of genotoxic DBPs representing the different chemical classes. In all, this experiment successfully identified the priority DBPs in different disinfected water samples. Next example of a real-world application was the experiment title named Development of a Automated Multi-Injection Shotgun Lipidomic Approach to a Triple Quadruple Mass Spectrometer. First, the purpose of this experiment is that shotgun lipidomic is a well-suited approach to monitor lipid alteration due to its ability to scan for varying lipid types on a global class and individual species level. However, the ability to perform high-throughput shotgun lipidomics has remained challenging due to its time-consuming data processing and hardware limitations. Why quadruple mass spectrometer? The automated multi-injection shotgun lipidomics approach was developed using a Agilent 1100 LC autosampler and triple quadruple mass spectrometer. By creating automated multi-injection approach, the reproducible lipid scanning period of 2.5 minutes. This approach also constructed to be the most cost-effective by using common LC instrumentation and customizable as the data acquisition period can be tailored to perform different scan types, period lengths, and scan numbers. What were the samples used in this experiment? For standard preparations and lipid extraction, LPLC grade chloroform and methanol were used. The data were presented where the first graph illustrates the total number of average lipid scans required to produce a reliable signal intensity and reproducible spectra. The different scan numbers were obtained by changing the sample injection amount and the total acquisition time. The second graph shows the intensity ratio obtained by the manual and automated multi-injection shotgun approaches for lipid extraction. In all, this experiment concludes that all automated multi-injection was more effective than the manual multi-injection. Thank you, and this was our presentation.
Thank you so much for joining us.